question about what we have discussed before the break? Okay. By the way, do you know from where this word or term Monte Carlo has come? Why it is called Monte Carlo techniques? Anybody knows that? It's a very strange name. This word Monte Carlo is actually name of a place, you know that, right? In France, right. And why is it famous? Casino and gambling, okay. So, but why this term? Do you know the history of, but who first used this term? Anybody knows that? For the things that you do in Monte Carlo, what do? You essentially generate from a distribution. You simulate a distribution. That's what is Monte Carlo all about, okay. So, who first used this term? You have any guess? No, Hastings used it for Markov chain, okay, but the Monte Carlo, the first use of the term Monte Carlo is actually linked to the nuclear bomb project in Los Alamos, okay, but do you know who used that term, or who invented that term rather, for this kind of mathematical operation? There is a very famous mathematician, von Neumann. It was von Neumann who first used this term. But the idea came in a very interesting way. So, for this nuclear bomb project, they had many famous scientists, including some very famous mathematicians in the project, okay. And von Neumann was there, and also the famous mathematician Stanislav Ulam. Ulam was there, okay. Now, it was a super classified project, so all these scientists have to live in confinement, okay, and they had no permission to communicate with the outside world, and that made a lot of people very depressed, okay, because that had an effect on their social life. And Ulam became very sick from time to time, and so he was sort of confined in his quarter, and he used to play cards with himself. So what kind of card game you play with yourself? There is only one card game that you play with yourself, okay. What is it called? Solitaire or patience, okay. Now in solitaire, all of you are familiar with that game solitaire, right? And you know that why is it called patience? That because most of the time you are not able to complete the game, right? It sort of prematurely terminates, okay. So Ulam was interested in this question, that suppose we start with a randomly shuffled deck of cards, what is the chance that I will be able to complete the game? So he was interested in this question, okay. And he was trying to analytically work out the probability for that. And it became a very difficult problem, and Ulam couldn't work it out, okay. So if you are not able to work out the probability, what will you do? Yes, that's exactly what he realized. So when he was trying to do some calculations, he thought that whether the calculations are correct or wrong, he can try to verify that, and he got this idea that maybe I'll randomly shuffle the card again and again and see how many times I get a particular combination of cards, okay. So that immediately became a very useful idea for other scientists who are working there, because the physicists at that time had some problems where exact computation was very difficult, okay. So they had some very complex differential equations and integral equations for which the analytic solution, even the standard numerical solutions were very difficult, okay. So this gave them an idea. Like for example, when you are trying to evaluate an integral over a very complex region, if you can do it analytically or by some numerical method, fine. Otherwise, you can use the Monte Carlo, right? You can randomly generate points from that region and average the integrand over that region. That's the standard technique. This is called Monte Carlo integration, okay? So Ulam's discovery or Ulam's realization gave them away, okay? Now, why this term Monte Carlo? That has a very interesting history. So everything I said was super classified in that project because it's the nuclear bomb project in the United States at that time, okay? So even for this method, they wanted a secret name, okay? So they wanted to call it by a name so that nobody will understand what it is, okay? And von Neumann gave this name because Ulam had an uncle who used to go to Monte Carlo to gamble, okay? So von Neumann started calling these methods Monte Carlo methods. So that is the beginning of term Monte Carlo, okay? And it is linked to, again, this nuclear bomb project in Los Alamos. So it happened in 1946-47, around that time. Okay. So the method was originally sort of invented by Ulam, but the naming of the method is due to von Neumann. Okay. Anyway, so let's look at this Gibbs distribution or Gibbs-Boltzmann distribution. Okay. So I said, what can you say about this distribution for large beta and small beta? For example, suppose beta goes to 0. Beta is a positive constant. I let beta go to 0 plus. What happens to this distribution? That is very easy. Uniform distribution, right? So for small beta, is nearly uniform. What happens for large beta? Suppose A has only 2 points, X and Y. Can you answer the question then? Degenerate at which one? So suppose A has only 2 points, X and Y, and you look at the value of Fx and value of Fy. Let's say they are distinct. So one is larger and one is smaller. So you said it will be degenerate. So it is going to be degenerate to which one? No. Fx is positive. Why near to 0? So in the set A, you have only 2 points. Let's say 1 and 2. So F has 2 values, F1 and F2. My question is, you said it is going to, is that clear that it is going to be a degenerate distribution? Why do you think it will be a degenerate distribution? Why do you think it will be a degenerate distribution? Denominator will also go to 0. So it's a 0 by 0 kind of situation. So you can't argue like that.
For two given points.
Yes. So let's say I have A equal to 1 and 2. So let's say F1 is smaller than F2, and they are both positive. I'm considering only positive functions for the time being. So what will happen to these as beta goes to infinity, say? You are right. If I just look at numerator and denominator separately, they both go to 0. But what happens to the ratio? See, there is something that is going to happen to the ratio for sure, right? Because it's a proper probability distribution. It adds up to 1. What will happen? Can you do the calculation for a minute or two and check what happens? I have told you that F1 is smaller than F2, and so you should be able to check what happens to the limit. So you have to do some adjustment here, like dividing the numerator and denominator by something so that this 0 by 0 form is no longer there, and you can calculate the limit. Yes, what happens? You have to do all these things. There are only 2 points, so it's very easy. Just try to use some direct calculation. Yes? Yes? Yeah. So what is your final answer? What happens to this as beta goes to infinity? It is degenerate at 1, right? It puts probability 1 at 1 and probability 0 at 2. Now, if you go through that calculation, and I now tell you that A has, say, S points, and again F1 is the smallest. Same calculation, what will it tell you? Suppose F1 is the smallest and all others are strictly bigger than F1. What will happen as beta goes to infinity? And again the same logic will tell you that it will be degenerate at 1. So whether you have 2 points, 3 points, 100 points, it doesn't matter. So the Gibbs distribution, when beta goes to infinity, will converge to the degenerate distribution at the minimum. Now, if it has two values where it is minimum, suppose f1 and f2 are equal and they are the smallest, what happens then? Yes? 1 by? Suppose f1 is a minimum, suppose it doesn't have a unique minimum. Okay, suppose f1 is a minimum and f2 is also a minimum. And then the rest are all bigger than f1 and f2. Half. That's what is going to happen, exactly. So what will happen is that, so if I ask you now this question, what happens to this expression as beta tends to infinity, what is your answer? It's going to converge to not degenerate, but uniform. It may be degenerate, but it may not be degenerate if it has multiple minima. It will converge to the uniform distribution on the set of minima. Okay. So the mathematical physicists say it in the following language. For them, beta is something that is related to reciprocal of the temperature. So beta going to infinity means what? Temperature is going down to 0. Okay. And so they say that as you cool the system down, the Gibbs distribution becomes uniform distribution on ground states, that is the lowest energy states. F is the energy function for mathematical physicists, I told you. Okay. So it is the uniform distribution on the lowest energy states. So this is something that they had from their physical intuition for a long time. Okay. So now this gives a very interesting tool. If I can somehow generate from this distribution for very large beta, that will help me to extract the minima of f. So if I have a minimization problem where it's a minimization over a finite set, but f is suppose very complex, okay, like many combinatorial optimization problem. In fact, the first application of this technique was by a Czech mathematician, his name was Cerny, and he used this idea to solve the famous traveling salesman problem. You know, the traveling salesman problem is one of the very famous problems where this like you have different spots that the salesman will have to travel, and you want to design a path so that the total distance traveled is minimum. Okay. So what is a path? A path is essentially a permutation or an arrangement of different spots that he has to visit, and so he goes from the first spot to the second spot and he travels some distance. Then from the second spot he goes to the third spot and he travels some distance like that, and then you add up the total distance, and that is the function that you are trying to minimize. So all these different arrangements of these spots are forming your state, right? So what does A consist of in that case? These different ways the salesman can travel, different paths the salesman can follow. So there are finitely many. And what is F? F is the total distance that the salesman follows. And so instead of evaluating the total distance over all possible paths, Cerny said, let's use this Monte Carlo Markov chain simulation. So Cerny's idea was somehow we should be able to generate from this Gibbs distribution where Fx will be the total distance traveled. And it's like you will start from one choice of the path and then use your Monte Carlo to generate the next path, and every time you generate a path, you will evaluate your Fx. So you are not evaluating Fx for all the paths. You are evaluating Fx only for the paths that you are generating by your Monte Carlo method. And you expect if you do it a few times, you will be hitting the minimum. So if beta is large, that's what is going to happen. Well, all this sounds very nice, but the question is that given a function f, how do I generate from this distribution? If I want to do it in the most naive way, then I first have to calculate these probabilities. And calculation of this probability involves this big denominator. And if I have to calculate this big denominator, then I have to evaluate all the effects. And then there is no saving on my computation. So somehow I have to find out a way so that I can generate from this distribution without calculating this big denominator. So that is the challenging problem that Cerny solved using Markov chain Monte Carlo. If you can evaluate the denominator, that means you have to calculate all the fx's. Then there is nothing to be done after that because you have evaluated all the values of f. So you can make a list and find out where the minimum is. That is exactly what you want to avoid. You don't want to evaluate the total distance that the salesman travels for all possible paths. That will be a huge task. So let's see now how we do that. So let's note this down first here.